which means if I want to make a 5-carbon molecule and I'm a plant, I have to do this loop 5 times. For 5 carbon fixations equals 5 new carbons equals a 5-carbon molecule. Okay? All right, so in a nutshell, this is the carbon fixation reaction. So we've done the energy transduction reactions. Now we've done the carbon fixation reactions. Now let's go ahead and do is kind of show the dark side of things, or what I hinted at before, which is plants are starved for CO2. There's not enough of it. And because there's not enough of it, the enzyme that's used by all photosynthetic organisms has a problem. And that problem is it can pick up a carbon, we would call that carbon fixation, or it can pick up an oxygen, in which case that's not carbon fixation. We have another name for this. Okay? So here is my RUBP, there's my enzyme Rubisco, and if Rubisco grabs a CO2, which we would expect it to do, we would get photosynthesis, which is the 2 PGAs being converted into 2 PGALs, and everything's fine and dandy. On the other hand, if the RUBP picks up an oxygen instead of a CO2, we get something called photorespiration. Photorespiration, from the plant's perspective, is bad. It's really bad. Because instead of getting 6 carbons to work with, I still have the original 5 that I started with. 3 that are found in a PGA that can be used in the Calvin cycle, and another 2 oxygens left over that make this molecule called phosphoglycolate. Now, what the plant could do is say, well, I screwed that up. Why don't I just take my phosphoglycolate and throw it away and start all over again? Well, it couldn't do this for very long, because every time it would throw away a phosphoglycolate, it would throw away carbons that it previously fixed in the past. And if the percentage of oxygen in the atmosphere is 21%, and the percentage of CO2 in the atmosphere is 0.04%, which molecule is that enzyme Rubisco going to bump into more often? It's going to bump into that one more often. And when it bumps into this one more often, it means the expectation is the plant's going to be doing a lot more photorespiration than it is photosynthesis, which means every time it does this, if it threw this away, at the end of the day, it would be in the negative for carbons, right? It would have lost more than it fixed. Okay? I'd be bumping into oxygen much more often and losing the carbons, and every once in a while fix one and then lose a bunch more. Okay? So what's happened over evolutionary time is probably that in the grand old days when photosynthetic organisms showed up on the planet, there wasn't any oxygen in the atmosphere. And there was lots and lots of CO2, and they developed this enzyme, RUBP, carboxylase/oxygenase, Rubisco. They developed this Rubisco enzyme to be able to grab a hold of CO2. And then it worked so well that everybody used it, until we're at the point where everybody uses it now. But in the meantime, the atmosphere has changed very dramatically. There used to be a lot of CO2 and not any oxygen, and now there's a lot of CO2. Whoops, I did this wrong. This is 21%. What am I doing? It's not 0.21. It's 21% oxygen in the atmosphere. Got my decimals wrong here. There's a lot more oxygen now than there is CO2, so we've done this flip. Lots of CO2, a little bit of oxygen. Now it's a lot of oxygen, a little bit of CO2. So folks have wondered for a long time, well, why is it that plants have not evolved any other means of doing carbon fixation? Well, it could be because there isn't any genetic variation for this trait, this enzyme, which would seem kind of silly because we've had 2.5 billion years of life on the planet to work this out. I think we could have worked it out. Currently what people think is that carbon dioxide is grabbed by Nabisco by grabbing the oxygens. And this probably has the same shape as oxygen does, and therefore any change in Nabisco to make it better able to, or less able to grab this, would make it less able to grab that. So currently plants are kind of stuck in this world where they're going to lose carbons based on photorespiration, and then the question is, well, what could you do about it? Well, one option is to try to get the carbons back, and that's using what's called a salvage pathway. A salvage pathway is an attempt to get the phosphoglycolate back to RUBP or PGA or PGAL that I could use, but how am I going to do that starting with that original phosphoglycolate? So it looks like what plants have done is used existing biochemical pathways to do this. And this pathway is called the salvage pathway. The salvage pathway involves three organelles: the chloroplast, the mitochondria, and the peroxisome. Don't want you to know the details here. I'll point out exactly what you want to know as part of this process. Here is the Calvin cycle as we've already done it. If it picks up CO2, we make PGAL, and we make everything we want to make. If, on the other hand, you pick up oxygen, you make phosphoglycolate, which gets converted to glycolate. Now, what do you do with glycolate? Well, it turns out there's a pathway that can convert glycolate into glycine, and that exists in the peroxisome. Glycine is an amino acid. It's an amino acid synthesis pathway that we're co-opting here. The glycolate is moved to the peroxisome, and then we convert it to glycine. The glycine is then shipped to the mitochondrion, and we have another biochemical pathway that converts glycine, the amino acid, into serine, the amino acid. Another amino acid synthesis pathway. And as part of this process in the mitochondrion, two things happen. The first is I make NADH, and the second is I lose a carbon as CO2. I lose that carbon. So already the plant has lost one of the carbons that it previously fixed in the past. It's going to have to refix that carbon in order to use it in the future. The serine is then moved back to the peroxisome. We go back through a pathway that converts serine to glycerate. It's like a backwards amino acid synthesis pathway. And here we use NADH. So the NADH I made there is offset by the NADH I lose here. That's a wash. Then the glycerate is converted to PGA using ATP. So in the salvage pathway, two things happen. You lose a carbon as CO2, and you lose an ATP. Does that make sense? So I started out making 2 carbons here instead of 3, and by the end of my salvage pathway, I got to keep one of those carbons, but I also lost a CO2 and I lost an ATP. So this is a cost. It is a cost to the plant of doing this photorespiration process. It's a cost that is assumed by the plant because the enzyme is capable of fixing oxygen just as well as it is of fixing CO2. Okay? Makes sense so far? All right, typical plant. Take an oak tree, that same oak tree we talked about last time, 100, 150 years old, sitting in abundant water. Let's say during the course of the day, it fixes a certain number of carbon dioxide molecules. Let's say, this is really a small number here, but let's say it fixes 1 million carbons from 1 million CO2 molecules. How many of these carbons will be lost here? Roughly half of them. Of the carbons that are fixed during the day, half of them will be lost to photorespiration. The other half will be kept and used to make biological molecules, which always makes me think plants would grow a lot faster and get a lot bigger faster if they still lived in that world 450 million years ago when there was a lot more CO2. That now, even though they can take up a lot of CO2, they lose a lot of it through this photorespiration process. They grow slower. They produce less fruit, less seed, because of this whole problem of photorespiration. Okay? All right, so what I'm going to do is go ahead and stop here. I just have a small little bit to do, which is to show you that there are some plants that have, I don't want to say solved the problem, but they've minimized the problem of photorespiration through some adaptations that we'll find elsewhere in this biochemical process. They're still going to use Rubisco, but they have another trick for dealing with the problem. All right? So I'll see you next time. Take care.